Um, so today we begin with a quite different topic, but in the end you will find out that they're all somehow connected with one another. In particular, we will see today probably we will also have to we will not be done by today, but about some elements of advanced electromagnetism, in particular electrodynamics. So what are they? I believe that this is going to be a mixture of topics that some of which you already met, some others you didn't, and also depending on the people, because as I said at the beginning of this course, you have different background because things are changing in the undergraduate program. Nevertheless, this is just a list. You might recognize something familiar to you and something less familiar. Essentially, we will adopt a classical approach, classical in the sense of non-quantum mechanic approach, to derive essentially what we are mostly interested in, which is the radiation emitted by charged particles which accelerates. So in different regimes, both for particles which are non-relativistic and also relativistic particles. And in particular, and then we will see, once we understood what's the radiation produced by a single accelerating charged particle, we will see an ensemble of particles and within some given approximations. So this is kind of part of the an important piece of the course entirely devoted to advanced electromagnetism, which is particularly relevant. So it's very general, but this is particularly relevant to what we will be exploring in a more astrophysical context. Okay. So let's begin with Poynting's theorem. What is that? Well, first of all, let's define the so-called Poynting's vector. So, which is just E vector H, so the magnetic field, so electric field vector times in the sense of vector product, the magnetic field, and C over 4 pi is the typical normalization constant that you have in the CGS. So I remind you that in particular in the Gauss system, that's the system we, as I told you in one of the first lectures, this is the system we will be adopting in this treatment of the electromagnetism. So this is just the definition of a vector. We will see in a moment the meaning of this vector, the meaning of the Poynting's vector. So let's work out the divergence of something similar. Well, except for C over 4 pi, this is just the Poynting's vector. So let's exploit in particular what you see here is just a vector calculus identity. And so the divergence, so nabla scalar, if you want, divergence of a vector product, you can decompose, you can express it as a, well, if you remember the rule of the mixed product between vectors, that's reminiscent of that, if you remember the rule. Of course, you have to take into account that divergence has something to do with derivatives. So when you derive a product, you have twice as many terms. And of course, it has to be anti-commutative. If you swap E and H, of course, the result has to change sign, which is exactly what you find here. Anyway, this is just a vector, as I said, vector calculus identity. So it's understandable if you are familiar, as you should be, with vector calculus. And why is this interesting? Well, let's have a look at the first term among brackets here. This is the curl of E. The curl of E, if you remember Maxwell equations in the Gauss system, in the Gaussian system, well, this is just what lies among brackets is just Faraday's induction law. So the curl of E is just minus 1 over C partial derivative with respect to time of B. just like that. Okay, so I replace this guy applying the Maxwell equation, which correspond to Faraday's induction law. Okay, easy, should be easy. Probably just mind the terms that are due to the choice of the electromagnetic system. As I said, we are in the Gaussian system, so this is just E and B, by the way, are homogeneous, so this guy is just 1 over C, minus 1 over C, partial derivative of B with respect to time. Minus E, what? Well, if you look at this term, the curl of H, and you remember, again, Maxwell equations, in particular, Ampere's law. Ampere's law is just 4 pi over C J, current density, plus 1 over D, D over T, partial derivative, time derivative of D. I remind you that this is the most general case in which we consider the possible presence of a medium. In the end, in the context that we will be interested in all the time, particularly in astrophysics context, we will be considering just the vacuum, so no medium, so no dielectric or magnetic properties. In particular, if you want to just to get back to from the magnetic field H, what I should call magnetic induction, but as a matter of fact, we call it magnetic field as well. There is a factor of 1 over mu, where mu is the magnetic permeability. Mind that this is just a relative, this is just a number, so this is relative to vacuum. So when you are in the vacuum, when you are considering vacuum, as we will be doing most of the time, mu is just 1, okay. So the two are the same in vacuum. As well as D epsilon E. Well, epsilon is again the relative dielectric constant relative to the vacuum case. So again, when you consider the vacuum case, both epsilon and mu are just 1. So just replacing these values, instead of H, I can think of B over mu. You see, you've got here B scalar its time derivative, but a vector times its derivative, you can express it just the derivative of the square modulus. We saw it just from the very first course on basic physics that most of you saw with myself. So if you think that B square is just B scalar B, you see that you can express the time derivative of B square as B vector times time derivative of B. Of course, you have to add an extra factor of 1 over 2, because the derivative of the square modulus gives you an extra factor of 2. Just like that. So I hope this is not too hard to see. The second term, well, the first term is I just copied. So the scalar product between the electric field and the current density J. And the second term, again, I replaced, instead of D, I put epsilon E. So here I have the analogous case as for the magnetic field. I have electric field scalar its time derivative. So you can express E time partial derivative with respect to time of E as partial derivative with respect to time, or just time derivative of modulus squared of the electric field, okay? And again, you gain an extra factor of 2 at the denominator just to compensate the factor of 2 coming out of this derivation. Just like that, okay? So this is pretty easy, I would say. Now, the goal is to make, if you look at the left-hand side of this equation, we want here the pointing vector to show up. So you just have to multiply by C over 4 pi, just like that. So of course you have to do the same also on the right-hand equation. So if you multiply, for example, let's take the middle term here. If you multiply by C over 4 pi, you just see that you just end up with minus J scalar E, just like that. Of course, the scalar product is commutative, so like I can swap both. Let's have a look at the other two terms. Well, you see you have the speed of light at both denominator, both terms, so multiplying by c over 4 pi just vanish. And you have in both cases at the denominator 2 times 4 pi, so 8 pi at the denominator, just like that. And then you can collect both terms. Here you have the time derivative of b squared over mu, and that's the same guy here. And here you have the time derivative of e squared over times epsilon. And here it is. Of course, both have sign as minus sign, so you just collected the minus sign. Why is this interesting? Well, because you can rearrange just this very equation. For example, by bringing, you see, the last term here on the right-hand side of the equation, you put it on the left-hand side of the equation, just like that. No other changes. And you end up with this very important equation. What is that? Well, this allows us to interpret the meaning of this result. Provided that if we call with U the energy density, so energy per unit volume, associated with the electromagnetic field, you see that you have the partial time derivative of energy density, so everything that I put among brackets is U, energy density. We will see in a moment why the newly defined Poynting vector is energy flux. It's a flux of energy. Flux means something crossing per unit time per unit surface. So this is energy flux, so it is energy per unit time per unit surface. Why is this? Why does the Poynting vector have this meaning? Well, if you look at the right-hand side of this equation, you see that here I wrote J scalar E is nothing but energy per unit time and volume used by the electric field in accelerating charges. Why? Well, if you think that J is current density. Current density you might think of as the product of the charge density, rho, if you want, times V, the velocity of the charges. Well, this is a very general expression in physics. When you have current density, which might refer not necessarily just to electric charges, to whatever, mass density, for example, also in the case of mass, you can define the same quantity. You can think of the volume density of that quantity times the velocity. Also from a dimensional point of view, if you think, J, what is J from the dimensional point of view? Is charges per unit surface per unit time. It's a flux of charges. So this can be seen as J is rho times V, where rho is the charge density and V is the velocity of the charges. Why is this? Well, if you think to replace J with rho V, rho E is charges electric field over volume. Charges electric field is forces per unit volume. So rho E is the forces felt by the charges due to the electromagnetic field per unit volume. So it's a force per unit volume times a scalar V. If you remember from your very first exam about physics, basic physics, when you have that scalar product between force and velocity, that's the power acting on what is acting the force. Here we have force per unit volume, scalar forces, scalar velocity. So it means that we have power per unit volume exerted by the electric field on charges. Is that clear? Okay. So if you want me to say it again, no problem. So J scalar E, you can also appreciate this from a dimensional point of view. Again, I said J is charges per unit surface per unit time. What is that? This is a vector. So you can, if you consider an elementary surface perpendicular to J, it means the number of charges crossing, moving in that direction per unit time per unit surface of this surface. Okay. So again, if you think of J as rho times V, as I said, this is nothing but the power per unit volume corresponding to the power spent by the electric field in accelerating the charges. Because, oh, you see, I didn't bother write this, what I've just said, just by speaking, but I hope this is clear. So we see that if you think of a generic continuity equation, you remember that the continuity equation of everything that you have in mind, which is just filling up given volume and which is moving in this volume with time, you have that the density, the continuity equation is just the time derivative of the density of this quantity, this generic quantity, plus the flux. If you consider, for example, just defining a closed surface, so a volume which is just, whose boundary is just a closed surface, might wonder what's the rate of change. So rate of change is the change per unit time of the amount of some generic quantity within this volume. Well, that's just, of course, the time derivative integrated over the entire volume, but you have to take into account how much of this quantity is just flowing out or flowing in across the surface. That's exactly this equation. This is a continuity equation in which you have the amount of the rate of change of energy per unit time, which is this guy. This guy tells you the rate of change of energy per unit time, per unit volume, plus what you lose because something is flowing out, the divergence. If you think of Gauss-Green theorem, that should be clear. If you want the flux over an entire surface, you have to integrate in the volume within the closed version, the scalar quantity, which is the divergence of the flux. So plus the divergence of S is what? Is equals the amount of energy minus J scalar E is the amount of energy spent by the field in accelerating particles per unit time, per unit volume. So it is how much energy the electromagnetic field loses per unit time, per unit volume. Loses because it spends this energy in accelerating particles. So because of conservation of energy, of course, this is energy which affects the content of energy density associated to the field. The greater J scalar, let's suppose J scalar E at some point is positive, in some point in space at some time, it means that charges are accelerated, are being accelerated. So the energy content of the associated electromagnetic field is decreasing somehow. And the balance is here on the left-hand side. The overall amount of what you lose, the rate of change, is just how energy density changes plus the divergence of its corresponding flux. So you see that if you think of a generic continuity equation, you immediately appreciate the meaning of the Poynting vector. The Poynting vector is indeed something which is telling us the flow. It can be outflow, can be inflow, depending on whether the divergence of S is negative or positive. But it tells you the flow of energy. So it's an energy flux. As I said, this is a very general, in this specific case, it's the continuity equation. So it's an energy conservation law. So you see that this is telling you that energy is conserved, and in particular, it tells you the energy density associated to the magnetic field and the energy flux associated to to an electromagnetic field. So it tells you two things very important. How the energy density associated with an electromagnetic field depends on both terms. In particular, as I said at the beginning, we are particularly mostly interested in the vacuum case, so both epsilon and mu, just one. So the energy density in the Gaussian system is just E squared plus B squared over 8 pi. This is very important to remember. So this formula for the energy density associated with the electromagnetic field. So first thing to know, we learned that when you have an electromagnetic field propagating, there's an energy content associated. And somehow we know that because we know that electromagnetic waves are propagating energy. So if there is something propagating energy through space and time, it means that there has some energy density associated. That's exactly what we found. And in particular, S is the flux of energy. So energy per unit area, per unit time, which is flowing. And this is conserved, of course. It's an energy conservation law. Yes, because the energy content, the energy carried forward by an electromagnetic wave can decrease or increase depending on the sign of the work done by the electric field on charges. Of course, this is just the electric field because we know that magnetic field cannot make work. This is constantly perpendicular to the velocity of charges. Okay, so the Lorentz force, of course. So this is very important to remember. It's interesting to apply and to calculate these quantities, so energy density and the Poynting's vector, so Poynting's vector, energy flux, to some very important cases. One solution, which is extremely important of Maxwell equations, is plane wave or planar wave. So wave whose front is just a plane, planes. In this case, we will see that, again, the solution is kind of, in the kind of plane electromagnetic wave, we will see that both electric and magnetic field are just perpendicular to one another, and in particular, they are both perpendicular to the direction of propagation of the wave. It's very handy to use the imaginary notation. So instead of using the sine cosine, I use as I said, the exponential of the imaginary quantity. This is handy, but what is its meaning? Well, electric and magnetic field are real quantities. So the assumption here is that we will carry out all the calculations using these imaginary quantities. But whenever we need to think of something real, as these fields are, we have to think just of taking the real part of it. Okay, this is just the common assumption. Calculations are made in the imaginary plane, but it means that when you have to think of a physical quantity, just think of the real part of it. Easy. Because derivatives are much easier and calculations are easier. So let's start by applying once again, Faraday's induction law, which I remind you is curl of electric field equals -1 over c time derivative of the magnetic field. Here I just rewrote Faraday's law just by replacing both formulae. Instead of E, I put what I wrote here. In particular, you will notice that I chose as unity vector A1 the direction of the electric field, and A2, unity vector A2 as the direction of the magnetic field. K, what is K? Well, K is the wave vector, which is telling you the direction of propagation, and immediately see that the argument of the exponential is constant over planes. a plane is at a given time. If you fix time, a given plane is, of course, identified by the scalar product between r, the vector position, and a fixed vector, which is in this case is k. So within a given plane perpendicular to k, the argument, a fixed time, of course, the argument of the exponential is constant. So all the points here belonging to this plane have the same value for electric and magnetic field, just because of the phase, the exponential is the same. Omega is, of course, the pulsation. We are talking about waves. So if you just replace this, what's the goal? We want to understand the relation between, first of all, the directions of the two fields, and also the magnitude, the modulus of both the electric and magnetic field. So how can you do that? Well, just by demanding that they, of course, satisfy Maxwell equations. In particular, we started with Faraday's law. So you see that here there's the vector. So the information on direction is just provided by the two unity vectors, A1 and A2, which are fixed. Here we have to work out a curl, so something with respect to r, with respect to the position. So let's focus on the first term. I have to work out this guy. But if you remember, the curl is conveniently written as nabla vector, because you can just work it out as by treating nabla as if it were a vector itself, whose Cartesian component was just the partial derivative with respect to x, y, and z, and just the second vector. So you just treat it just as a typical, as a standard, as a normal vector product between two vectors. But now look. If you pay attention to the way it works, you have all, I have written here A1x, A1y, A1z, so the three Cartesian components of the generic unity vector A1, which gives us the direction of the electric field. If you think for a moment, you see the action. Well, when you partial derive with respect to a spatial component, one of these three guys, k scalar r means kx x plus ky y plus kz z. So whenever you partial derive with respect to a generic xj, by xj I mean it could be x, it could be y, it could be z. Okay, just a synthetic way to you see that essentially when you derive this scalar product, you just gain an extra factor of kj, the corresponding kj. So it means that when you derive with respect, you gain from the exponential, you gain just an extra factor of, if you derive with respect to xj, you gain just an extra factor of I kj. It takes just a few seconds to realize the gain. So it means that this can be rewritten this way. Indeed, it works like a vector product between the vector ik and the remaining thing. So you can just summarize it just by writing this way. So nabla vector is just ik vector, the same guy. That's why the exponential, you see, is very useful, because we are exploiting the property of derivative, of deriving exponentials. So and of course, so this settles the left-hand side of this equation. If you now pay attention to this right-hand side of this equation, you just have time derivative. The time derivative, look at the exponential. It means that you gain just a factor of minus I omega, just like that. And then the rest is just the same. So you see that by time deriving this guy, you just gain a factor of I minus I omega, so much easier than in the previous case. So putting together, so replacing both this guy and this guy here in the Faraday's law, you end up with this. Now, Here you have both, of course, the information about the directions and information about the magnitudes, the modulus. So let's look at the directions. You see that A2 is something parallel to K scalar A1. Sorry, not scalar, K vector A1. So if you apply the right-hand rule, K vector A1, you end up with A2, which is exactly what I show here in the figure. Okay, so indeed we see that since K is the direction of propagation of the waves that we started with, you immediately see that both are perpendicular. And the K, A1, A2, they all together form a right-hand triad. You can just, well, you can simplify here the both eyes, and you see that, okay, this is just, I just removed also the exponential dependence. So here I just rewrote what we had in the previous slide. So this is the result. You see that you can immediately work out the moduli of both sides of this equation, and you end up with, well, given that K is perpendicular with A1, the modulus of this guy is just K. A1 is just one unit vector. So E0, which is the normalization, so the magnitude of the electric field, essentially, the magnitude, well, it's oscillating, so it has minimum, maximum value. This is the maximum amplitude, if you want. You see that it scales with this way, with omega k and B0. Now, the interesting aspect is that you can do the very same calculations that we've been doing so far by considering now, instead of Faraday's law, Ampere's law, which is here among brackets. Oh, mind that we are in the case of no charges, no current densities. So J, if you think of Ampere's law in the case of J0, this is just right. This is just nothing but Ampere's law. Now, if you compare this case with Faraday's law, you see that you have the very same equation except for a minus sign. The Faraday's law is just the same as this one here by swapping B and E, except for a minus sign. It's just a minus sign. So it means that you can play the very same game we did so far, and you will be ending up, you will be coming up, you come up with the very same, except for a minus sign. But when you are interested in magnitudes of vector, minus makes no difference. So it means that here, this is the relation of the two magnitudes of the two moduli. So it means that you can swap E and B0, and you will end up with the very same result. Now, starting from Ampere's law. But you see that combining these two, this automatically means, for example, if you replace instead of B0 here, you put this guy here. So you have that E0 equals omega over Kc all squared times E0. But that means that, first of all, you obtain what we could call as the dispersion relation, because there is a relation between the pulsation of the wave and the wave vector, the wave number. And you remember that omega over K, which is in this case is just C plus minus C, is just the velocity of the wave with the given wavelength. And in this case, well, that's the simplest possible dispersion relation. There's no dispersion because all the waves, any wavelength, have the same speed, which is the speed of light. So first of all, speed of light, no dispersion, all the waves at any wavelength are traveling with the same speed, which is speed of light. We are in vacuum. And you see, the second important point here, the second important result, is that both electric and magnetic field have the same magnitude. That's exactly what this is something that I already foretold you in one of the first classes when I told you one of the reasons why, for example, the Gaussian system is convenient is because given that the two fields are homogeneous in a plane wave, the result is that they have the same magnitude. So this is also very useful for calculations. So we see that in the plane, in the case of a plane wave in vacuum, as I said, no dispersion. All the waves are traveling with the speed of light in vacuum, and both electric fields are perpendicular to one another, perpendicular to the direction of propagation, and have the same magnitude. We have a beautiful set of results important to remember. Same magnitude. You couldn't ask for easier results to remember. Now let's wonder about the energy flux. So the energy flux carried forward by the electromagnetic, by the plane wave. Well, it's just a matter, now we know it's just a matter of calculating the corresponding Poynting flux vector. So if you remember E c over 4 pi E vector H, which is B in our case, we are in vacuum. So it means E, except for a factor of c over 4 pi, this would be c over 4 pi electric field vector magnetic field. The two are perpendicular. So we know that, first of all, you see, the electric field is oscillating along A1. So we can think of just for a moment here, A1. The magnetic field is along A2. So you see that electric field vector magnetic field is just a vector parallel to K, which makes sense because indeed the wave is propagating along K. So the Poynting flux is parallel to K. And indeed, the flow of energy is taking place along K. So energy is flowing in the same direction, along the same direction as K, which makes sense. But the magnitude, what is that? Well, you have E squared, E0 squared, or equivalently B0 squared. But mind that this guy, well, I should have E squared, not E0 squared. But E squared or B squared is a function of time. In particular, is a sine or cosine. So here, so it's a function of time. But here, when I wanted to calculate, given that it's a periodic function as a function of time, this means just time average. The time average of sine square or cosine square, which is the same, you know very well, the average over a period is just 1/2, 1/2. So that's why here you have c over 8 pi instead of c over 4 pi. You gain an extra factor of 1/2 just because you are time averaging sine square or cosine square. Okay? You have the electric field is oscillating, so the magnitude of the electric field is not constant. This is oscillating as a sine. So the average over a period is just 1/2. That's where it comes from. So easy. So you immediately see the energy flux scaled with the square of the amplitude. But if you remember the way we define intensity, also in your undergraduate course, intensity is scales with the square of amplitude. You see, again, the same law in a different context. And what is the energy density? Well, again, it's a matter of calculating the formula that we saw in the previous slide. I told you energy density is E squared plus B squared over 8 pi. E squared and B squared are equal in this case. So it's just E squared again, should be E squared twice. But then when you time average, that's the reason why I put again this bracket. So just to mean time average, again, should be e squared over 4 pi, you gain an extra factor of 1/2 just because of the same reason, because you have time averaging. So we practically saw in this very important example of a plane wave both the flux, the energy flux, which is expressed by the Poynting's vector, as well as the energy density associated. These are time averaged because both fields are oscillating, so are changing as a function of time, but in a periodic way. So you can just, it makes perfect sense just to calculate their time averages. And if you compare the two, you immediately see that the energy flux can also be seen as energy density times c, the velocity with which waves are propagating. Again, this is a very general formula. Density of something, if you know that something is moving along a given direction with a given velocity, the flow, which means the flux, which means how much of this quantity is crossing the surface, the unit surface perpendicular to the line to the direction of motion, is just energy density times the speed. Again, you see, density, in this case, we are talking about energy. So energy density times velocity gives you the flux of energy, energy flux. Very general formula. And you can work it out if you think of the generic cylinder moving within a given unit time, crossing a given surface. You see that you end up with this very general formula, connecting the flow, the flux of something with the energy of that very something and the velocity with which it's propagating. So just for my own curiosity, any of you who already met Poynting's flux, or did you already met it? Okay, excellent. So let's move on. Let's make a step forward. Let's see the concept of electromagnetic potentials. You see that one of the Maxwell's equations, which is the divergence, the null divergence of the magnetic field, or if you want, this is just the fact that magnetic monopoles cannot exist. That is essentially the same information. Well, in general, you can think of a generic vector field. It's possible to show. There's also a theorem called Helmholtz theorem, which under some quite general assumptions on the vector field, you can think of the field as the sum of two different fields. One which is irrotational or curl-free. A field which is irrotational is by definition a field whose curl is 0, plus a so-called divergence-free field. So a field whose divergence is 0. So whenever you have a very general field, you can think that you can express this field as the sum of two different fields. One which is irrotational, so curl-free, plus one which is divergence-free. So you can play the same game, for example, having in mind the magnetic field. And you see that the magnetic field is divergenceless, is divergence-free. So it means that you just have, of these two possible fields, you just have one. One of them is just 0. One of them is 0. So you just have, so the divergence-free component. But again, from vector calculus, whenever you have a divergence-free field, it means that you can express that field as the curl of something, the curl of another vector field, which is exactly what we do here. So because of the null divergence of B, we know from vector calculus that there must exist a vector field which we call A, whose curl is just B. We will see that there's a whole class of, is not unique A. If you want a vector field whose curl is B, you will see that you have an entire class, not just one. So it's not unique A. But surely there exists at least one vector field A whose curl is just B. So this is just vector calculus. We call this vector field as the vector potential. So A is the vector potential. Let's consider once again Faraday's induction law. So the curl of E equals -1/c time derivative rate of change of B, which we exploited already repeatedly. Now, if you replace instead of B what we just obtained, so the curl of the vector potential, you see that you have the rate of change of curl of A. You can swap nabla and time derivative, so you can express everything as a curl of something. And this something is just the sum of the electric field plus 1/c rate of change of the vector field. But now, if you consider what lies within brackets, you have the curl of a generic vector field, which is this sum here. Well, if the curl is 0, it means that all this guy is curl-free, or equivalently is irrotational. Now we are in the opposite situation. Again, all this vector field belongs to the other class, to the class for which the curl is 0. So all this field is said irrotational. Oh, I didn't say here, but there's also another name, as in this case here, the curl is 0, you might speak in terms of irrotational field. There's also another word for the fields whose divergence is 0, so divergence-free or solenoidal, because you have something, the field lines, one of the easiest example of field lines of a field with whose divergence is 0 is that of a solenoid. Anyway, just a matter of name. But again, from vector calculus, we know that whenever you have a curl-free vector field, it means that there must exist a scalar field whose gradient is exactly that field. So it means that there must be a scalar field, which we call phi, and phi is indeed called scalar potential, much in the same way as A is called vector potential, whose minus gradient is exactly the guy for which we know the curl is 0. So again, from vector calculus, you have a field whose curl is 0, so there must exist a scalar field whose gradient is just this guy. Again, you can think that this is understandable if you think of Stokes' theorem. The line integral of a gradient as 0, because you are integrating, you are making a line integral of a gradient. So you start of a closed line. So the potential, of course, has the same value in the starting and final points. So the curl has to be 0, the curl of this guy. Okay, anyway, this is just a link to what you should know from your previous calculus studies. So we can express the two highlighted boxes, is something which we inferred the existence of two fields. One which is a vector field A, and we called vector potentials, and the second guy is a scalar field phi, we called it scalar potentials. So we found out that both electric and magnetic field can be expressed can be considered as a function of the combination of both these couple of new fields. Okay? Once you know A and phi, you automatically know everything about the electromagnetic field, because you know both electric and magnetic field. So now the general goal of determining, given some charges distribution, given some current density distribution, the general goal is of course, through Maxwell equations, to derive the corresponding electromagnetic field. Now we can shift the problem. Instead of deriving electric and magnetic field, we aim to derive these potentials, because from these relations, you know that once you know A and phi, you know automatically E and B. So now the problem is a different way of different formulations. The goal is to determine A and phi as a function of some known charge and density and current distributions, okay? Let's see exactly the equations that these fields have to fulfill. To see that, let's again consider Ampere's law. So Ampere's law tells us the curl of B equals all this guy here. And here I simply replaced, instead of B, just what B is. So the curl of A, so we have a double curl. And so you see that also E, by replacing E, the electric field in the second term, I first gain a factor of 1 over C minus 1 over C time derivative of nabla phi. So I can swap nabla and the time derivative. So I first do now time derivative of phi, nabla, so the gradient of this guy. And here you see time derivative of time derivative, so you gain an extra, a double time, the second time derivative with respect to time of the vector field. You see that I collected just the minus sign just because the minus sign is in both terms here. So now I have an equation which is just connects the two electromagnetic potentials. I have just A and phi, in addition, of course, to, in this case, to the current density. Now let's exploit another vector calculus identity, the double curl. The double curl, again, it's very useful because if you remember the double vector product, that works exactly in the same way if you treat nabla as a vector. So you see, the first scalar, the third, which scalar in this case is just divergence, and the second, so gradient of divergence of A minus double the scalar product between nabla and itself, so nabla squared, which is the Laplacian operator. You might know it also as Laplacian operator from Laplace. So just again, in the second term, the right-hand side of the equation, I just copied it. I didn't do anything special. Now we introduce a new operator which you might have already met. It is so-called the D'Alembert operator from the French, after the French guy. Pay attention, in some textbooks you might find the definition of D'Alembert as the minus of this guy. So in some textbooks there are first the plus sign with a second time derivative and minus Laplacian. Here I just adhered to the notation by the Rybicki-Leitman. I'm following quite closely the Rybicki-Leitman textbook in here. So it's just a matter. So remember that there might be some confusion. So do not be. So beware of that. So having defined the D'Alembert operator, you see that this by bringing here this guy, the Laplacian operator on this side, and putting all this guy on the other side here, you just end up with the D'Alembertian of A equals, well, this guy is gone on the other side here, and then you can collect, you see, you have the gradient of this and this. The gradient is, of course, a linear operator, so you can collect and the gradient, the sum of the gradients is the gradient of the sum, which is exactly what I did here. Now, let's make an assumption, or better, let's impose a so-called gauge condition, which in this case, we demand that both potentials must satisfy also this equation. This is called Lorentz gauge. We will see in a moment more in detail what this is and why this is plausible. So assuming this gauge between the two potentials, you see that all what lies within this in bracket is just zero. So you end up with a very simple equation, which tells you that the D'Alembertian operator of the vector field must be equal to minus 4 pi over c current density. I haven't proven yet the second one about the D'Alembertian operator of the scalar field. I'll do it in a moment. But just mind that if you look at the D'Alembertian operator definition, you see that this is nothing but the wave equation well, it's inhomogeneous, because to have a proper wave equation, the right-hand side of this equation should be zero. Okay. So this is just the wave equation in the inhomogeneous case. And this is something that allows you immediately to appreciate the usefulness of the Lorentz gauge. If you don't assume the Lorentz gauge, it's less. It doesn't look like that. To prove the second one, so to prove that also a similar equation must be fulfilled by the scalar field, so a similar wave equation, inhomogeneous wave equation, just consider, well, what I call the first Maxwell law, which is nothing but the Coulomb's law expressed in terms of Maxwell. So the divergence of the electric field is just 4 pi rho, charge density. So if you replace, instead of E here, the formula that gives you E as a function of the two potentials, well, just divergence of this guy here, but the first term is nothing but the Laplacian, minus Laplacian of phi, and here you gain an extra factor of, you can swap. Here I have divergence of time derivative, where time derivative of divergence, but divergence of A is, from Lorentz gauge, is minus 1 over c rate of change of phi. So you have in the end two time derivatives of phi, 1 over c time derivative of, so you see that this is nothing but the minus D'Alembertian operator. And this is 4 pi rho, so you end up with this too. So from a formal point of view, you see that we these two equations, so the wave equation ruling A and the wave equation that must be satisfied by phi, are a new way to express Maxwell equations. Because once you know A and phi, you automatically know B and E, and you automatically know, by the way we defined B and E, that also this equation, as well as Faraday's equation, are automatically satisfied. So finding A and B is an equivalent goal as determining the electromagnetic field. And understandably, they must depend both on the charge density as well as on the current density. In which way? Well, this very simple way. This is something very important that we will see. So we are kind of generalizing, moving to expressing the Maxwell equations in a different way. We will see in one of the next classes that we will make a step forward and express these very equations in a covariant way. By covariant, mean changing from one inertial reference frame to the other, expressing, because these are not covariant. So when you move to one inertial reference frame to the other, having in mind that you have to go through Lorentz transformations, these are not, this way are not Lorentz invariant. I said something about gauge transformations. What are they? Well, let's make this simple point. Let's assume you already know A and phi. As I remarked in the previous, just a few minutes ago, when I stressed the fact that they are not unique, they are not uniquely defined. Well, let's suppose that instead of A, you define a new vector field, which we call A prime, and this is defined as A plus the gradient of a generic scalar field, which I call here with capital lambda. So capital lambda is a generic scalar field. So I work out its corresponding gradient. It's a vector field, so I sum up. Now I tell you that if you define a correspondingly new scalar field, which I call phi prime, and I define as phi plus minus 1 over c time derivative of the very same scalar field, capital lambda, sorry. Well, I tell you that also this new couple of fields of potential is also giving you the very same couple of electromagnetic field. Let's see why. Well, to see that, let's consider A prime instead of A. So let's work out the curl of A prime. If what I just said is really true, well, I should end up with B, nothing but B. Let's see why. Well, if you replace just A prime, the definition of A prime, well, of course, the curl of A plus the curl of the gradient. But again, for the very same reason I told you in the previous slide, for a calculus identity, for a vector calculus identity, the curl of a gradient is 0, identically 0. But the curl of A is exactly B. So indeed, using A prime instead of A, you get the same magnetic field. But let's see whether the same holds also in the case of the electric field. So let's do the same exercise. In calculating the analogous of this guy, we have just to replace phi with phi prime and A with A prime. So minus gradient of phi prime is just minus gradient of phi minus minus, so plus 1 over c. And again, I swap the time derivative with respect to the gradient. So plus 1 over c time derivative of gradient of lambda. And then I have minus 1 over c time derivative of A prime. So minus 1 over c time derivative of A minus 1 over c time derivative of gradient of lambda. But you see that I have two guys that vanish, cancel out. So indeed what I'm left with is just E. So indeed this very easy proof tells you that indeed these potentials are not uniquely defined. Once you have a couple of them, once you have A and phi, you see that we didn't make any assumption on the scalar field, capital lambda. So it means that there's an entire class of scalar plus potential fields which give you the very same electromagnetic field, which is exactly what we care of. So in particular, this degree of freedom that we've just found is exactly what defines the gauge transformation. Okay. So it means that a transformation like the one we considered above, so moving from A to A prime and from phi to phi prime, we made a gauge transformation. This gauge transformation didn't change. You changed the potentials, but you didn't change the electromagnetic fields. So as I said, these are called uh, gauge transformations. So you can, to reduce, to further select all the possible family of potentials that give you the same electromagnetic field, you can impose further conditions that must be fulfilled by both potentials. And that's exactly what we've done in the previous slide when we assume the Lorentz gauge. We made a further requirement. And so depending on the gauge that you choose, so on the kind of further condition that you set that must be fulfilled by the potential, you make a further selection of all the possible gauge transformations. So you are restricting all the possible family to the family of fields that give you the same P and E and satisfy some further conditions. They are alternative. You can make alternative choices, and there are two the two most widely used are the one we've just seen, which is Lorentz gauge, and we exploited it just when we obtained the wave equations, the inhomogeneous wave equations for A and phi. But there's also an alternative condition, which is also pretty famous, which is the so-called Coulomb gauge. The Coulomb gauge, you see, it's different. So in the case of the Coulomb gauge, it's the divergence of A, which has to be 0. So A has to be an irrotational field. Okay, just sorry, no, not irrotational, divergence free. So solenoidal, if you want. Let's focus in particular on the Lorentz gauge, which is exactly the one which is mostly relevant to us. We will be using in the remainder of this class and also next classes. Let's explore a little bit more in detail. So the Lorentz gauge, the Lorentz condition which defines the Lorentz gauge is the one we already saw, and I here highlighted in this box. On the right, I keep reminding ourselves how electric and magnetic fields are defined as a function of the both potentials. Okay. You might wonder, is that the case that whenever I further set the Lorentz gauge, are then A and phi uniquely defined? No, you are restricting the possible, but you still have a family of fields that satisfy both, that give you both, of course, the same electric and magnetic field, and so all of them satisfying the Lorentz gauge. How can we see that? Well, for example, you can define, if you have A and phi, which already satisfy the Lorentz gauge, we can define a new A prime, plus, again, as we did before, by summing up the gradient of a generic scalar field, capital lambda, and again, the very same phi prime defining the very same way. But in this case, if we want the Lorentz gauge to be satisfied by the new fields, we have to impose a further condition on this scalar field capital lambda. Sorry, I keep saying lambda instead of gamma, which is this one. So provided that the generic lambda field satisfies the wave equation, this is indeed a wave equation with the speed of light, the speed of the waves. If you provide that you choose lambda this way, you will see that it's immediate to see that if A and phi satisfy Lorentz gauge, A prime, phi prime will also. So you see that again, the choice is more restricted in a sense, because now the function, the scalar field lambda cannot be anything but has to satisfy it. But again, you have a number. And all of these fields that satisfy the same Lorentz gauge, the same gauge, which is the Lorentz gauge, are called, so all these transformations, as the one I showed here, so this transformation with this field satisfying this equation is a Lorentz gauge transformation, because it keeps satisfying the Lorentz gauge condition. This gauge, so this choice of the family of potentials, if you want, satisfying the Lorentz gauge, is very important, is very relevant to us in particular. Well, in general, but in particular to us for two reasons. One, because something we already enjoyed, that the wave equations that must be satisfied by both fields are wave equations, or very simple, and especially they are symmetric. You see the results of both equations we have a very symmetric equation. Both the Lambertian, in one case, J connected with J, in one case with a charge density. So that's why here I wrote on equal footings. There, the Lorentz gauge ensures a more similar wave equation for the two fields. And the second one is very important because it's apparently invariant under Lorentz transformation. We will see when we will be treating all this stuff within covariant, with a covariant formalism, we will see that whenever your field, so your potential and scalar field satisfy the Lorentz gauge in one inertial reference frame, automatically the corresponding fields in a different inertial reference frame will be also Lorentz gauge. So the belonging to a Lorentz gauge for a given couple of fields is a Lorentz invariant property. This is not necessarily the case for other choices, for example, such as the Coulomb gauge. So this is something which makes it very appealing and very useful. Just to let you appreciate some very basic properties, characteristics of the Coulomb gauge. So if you make a different choice, instead of assuming the Lorentz gauge, you assume the Coulomb gauge, which is also known, you know the acronym AKA, probably I already used, but I didn't. You know AKA, what it stands for? Also known as. Okay, excellent. Okay, so so it's also referred to as the radiation gauge or transverse gauge for reasons which I honestly don't remember right now. But if you want to know everything, again, my first reference is the Jackson Classical Electrodynamics. That's the Bible of electromagnetism. So this can be interesting to explore a few things about this gauge. Again, let's start from the equivalent from Coulomb's law, essentially, in a differential formulation. So if the divergences of E, again, if you make the same, if you carry out the same exercise we did just in a couple of slides before, you can express divergence of E as this guy here. So I just replaced E here. So you gain the Laplacian minus Laplacians of phi. And again, given that we are in the Coulomb gauge, you see the time derivative of divergence of A is 0, just because of the Coulomb gauge. So this guy is nothing but minus Laplacian of phi. But you see, this equation should look very familiar to you. This is nothing but the Poisson equation. And you already know that, probably from Fisica 2, you should know immediately the solution, the formal solution. The solution to Poisson equation is just, you're essentially summing up the Coulomb potential of all the distribution of charges. So in a generic R, the resulting potential at a given position R at a given time t is nothing but the sum of all the Coulomb potential due to a generic amount of charge in a volume, in a given volume integrated over the entire space. This is indeed, as I said, the resulting scalar potential is instantaneous Coulomb potential. This is interesting because, as we will see next, one of the results of the solutions of the electromagnetic wave equations is that a change taking place in one point in space at some time cannot affect what's going on, so the electromagnetic field, at a different point in space. Because those changes, everything has to travel at the speed which cannot be greater than the speed of light. The fact that here...
Posso chiedere un piacere oggi
certo.
di finire entro l'1:20, massimo?
Ok, quindi fra 12 minuti. Okay.
Perché è un problema di sonificazione di aula.
Ok, non c'è problema, ok.
Grazie.
If you look at this expression, this formula, it looks like whenever you make this function changes at some point, the change at a different point in space is instantaneous. This might look like it contradicts what I've just said, but actually it's the solution in this case, it's deceptively simple, because actually phi change instantly. So the value of the scalar potential seems to violate this. But actually what you measure is the electric field. The electric field is not just phi, it's also A. So when you work out E, as a matter of fact, the behavior of A counterbalances this. So you have no more instantaneous change. So information traveling at a speed higher than the speed of light. If this sounds a little bit not so clear, that will become clear in the following. Yes, in this case, the corresponding wave equation of the scalar potential, in this case, is this guy here. If you compare with the, and yes, it is usually used in the case of no sources when you have no charges, and in the case of also no temporal dependence, or for example, of a charge distribution. This is also something. And in this case, of course, if phi is 0, and the electric field, you have just this guy here. I'm just going quickly here on this Coulomb gauge, because this is something we will mostly neglect, just for your knowledge. So just beware of that. And if you remember this, as I said, this look of the instantaneous Coulomb potential as something deceptively simple. I like this expression because it looks like simple. It looks like, oh, there's every change taking place at some point can instantly affect the potential at a different point in space. It's not like that. The potential, phi, yes, but what you measure in practice is not phi, is E and B. And we will see. So having less than 10 minutes, I have to rethink of what I'm going to say. One important thing, which I'm not going to prove, so I'm not going to prove from a mathematical point of view, because it takes quite long and it's not worth from this point of view of this course, is that if you are, let's go back to the Lorentz gauge, okay? So Lorentz gauge, these are the wave equations, the homogeneous wave equations for both potentials. Let's suppose you know J and rho. So how am I supposed to find the mathematical solutions for A and phi? Well, the solutions are these guys here. So, of course, both potentials are a function of point in space and time. And you see, these are integral of this stuff here. But you see that in the numerator of both formulae, there is the function, the corresponding function, both on one side, the current density, on the other side, the charge density, among square bracket with ret. Ret stands for retarded. What does this mean? Well, first of all, I just put the reference if you want to see the detailed mathematical proof. I'm not gonna go through it. Just have a look at section 6.4. What are these? Well, let's consider the retarded charge density function. Well, this means that for a given time t, for a given point in space r, this function has to be evaluated in all possible generic r prime. At what time? At a given time t prime, which is preceding the time t by an amount of time which corresponds to the light travel time between the 2 points in space. It's in the same, of course, for j. So retarded in the sense that if I want to calculate the retarded charge density here, having in mind this point r at this time t, well, the value of the charge density I take here in this point is not the value of this function at the same time that I'm considering here, but a previous time. How long previous? I have to work this out at the time which precedes this time t by the light travel time between the 2 points in space. So how long does it take for light to travel from here to here? 10 seconds. Okay, so rho here, I have to evaluate the function rho at the time t minus 10 seconds, because I have to allow light to travel from here to here. So what can affect the function here must have taken place here at some given time before. How long? Well, the light travel time. I have to allow the light to travel. Retarded in this sense. If one of you does something at some point, I will be affected. A delta t later, well, delta t is just the light travel time, because the information about the change travels at the speed of light. So if I am affected now by something that you did, what you did must have been done delta t before the time I received this. Retarded in this sense. This is a mathematical solution. So these functions within the integrals have to be evaluated at a different time. You see that if you change r and t, automatically the argument of the integral changes as a consequence, because all the light travel times change correspondingly. So that's the formal solution. Of course, then, as a matter of fact, it is as difficult as depending on the kind of charge density and current density you are dealing with. So this is the general solutions in terms of A, and that gives you both potentials once you know J and rho. And you see that you have to do with these retarded potentials. There's one very important case that we will care of, is that when instead of a generic charge and current density distribution, we consider just one single charge. So one point-like charge with a given velocity. Of course, given that you have one single charge and that the charge is moving, you both have one density charge, or charge density and current density. Let's see why. What it looks like. Well, the first equation, let's suppose R0 as a function of time is just the position of the charged particle as a function of time. I called R0 to distinguish from a generic R. Okay, so R0 as a function of time is the position of the particle, of the single particle. I'm considering a very special case, single particle as a function of time. So you immediately see that the density is the delta function. The charge is zero except for the very point at which the charge lies at some given instant. And of course, if you think of the properties of the delta function, this is just delta function, times Q, because Q is the charge, the electric charge of the particle, okay? At the same time, the charge density, the current density, if you remember what I said at the beginning of this class, is rho, charge density, times V, the velocity. In this case, I call U as R dot. Well, I should have written R0, sorry. There's a typo here. This is R0 dot. So U is just the velocity of the charge. So velocity times charge density, just like that. We will see on Wednesday, unfortunately, that the solution we will derive. We will start from the previous general solution. We will derive exactly the solution for the vector potential and the scalar potential for the case of a single charged particle. This case is so important that it has been assigned a given name after the people who first discovered this. And these are called linear Wiechert potentials. So linear Wiechert potentials are the potential in the special case of one single charged particle, just like that. I'm sorry, I have to stop. Any questions? Okay, so we carry on Wednesday.
Yeah.